One of the main goals of business companies and many organizations worldwide is to become much more data-driven, to be able to harness the power of up-to-date software tools, big data technologies, and cloud computing services. It's a combination of great software tools, interesting and useful data, and cost-effective virtual IT resources. Now, to be able to move in that direction, legacy software tools that are used to be deployed in private data centers are expected to utilize cloud services and become cloud-native applications. However, those existing applications were designed, developed, and maintained as one giant monolithic applications with a once-in-a-year software release cycle, maybe 2 times in a year. Every system upgrade is like a big project. This traditional development approach is not good enough. It's not supporting the required agility of a fast-changing business landscape. Software updates for enterprise applications should be released and deployed in weeks, days, and even hours. If a new software feature is needed right now, why should we wait 6 months for the next big software upgrades? So, over the last couple of years, a new software development approach called microservices emerged as a solution to cross that gap. Microservices are one of the biggest revolutions in the software industry, as they are the building blocks for creating cloud-native applications. My name is Idan, and I'm teaching multiple courses related to the topic of cloud computing. This training is designed to provide you a solid theoretical understanding of the microservices concept. We are going to talk about the challenges with the old school development style, which is called in a negative way monolithic applications, the industry definition of microservices, and the building blocks of a single microservice. Then we will be able to move to the macro level and talk about the concept of a microservices architecture, what are the key benefits and business value when using it. We will also review some challenges to keep in mind while considering this new approach, and lastly we'll review an interesting case study. This is our plan. Thanks for watching, and I hope to see you inside. Hi and welcome. Thanks for joining. My name is Idan and I will be your teacher. We are ready to start our hopefully interesting journey with the main learning topic in this course, meaning microservices. I like to explain a technical concept from multiple angles and specifically try to understand together the business case. What is the problem we are trying to solve, and only then move to the actual solution. In the Getting Started with Cloud Computing training course, we talked about the business case of moving enterprise application into the cloud, which is happening everywhere worldwide. There are multiple global cloud service providers like Amazon AWS, Microsoft Azure, Google Cloud, and others. We can pick one of them and in a few minutes allocate whatever needed virtual resources for a specific application. It can be by using the classical infrastructure as a service model, a platform as a service, and also function as a service. Practically speaking, almost any application can run somehow in a cloud environment, especially while using the infrastructure as a service model, which is actually running application on virtual machines that are in the cloud, in a public cloud service. That's great and useful, but there is a big question mark about the business benefits of moving a legacy application into the cloud. In most cases, those existing applications are not cloud native applications. They were not designed to reside in a cloud environment and fully utilize the features and options that are available in such environment. We will of course dig into that problem later. The good news is that there is a solution to that application design problem or challenge based on the concept of microservices. Microservices is a software development style or software architecture that is supposed to be used by developers when they develop complex, large-scale application, but not regular application. Microservices are the foundation of cloud-native application, which means this is a crucial topic to anyone that would like to understand the emerging new world of cloud computing, looking from the application point of view. Now, please don't worry if you are not a software developer. I'm not a software developer. And anyway, the main course objective is to understand the concept of microservices so people coming from a variety of backgrounds will be able to understand it without losing the big picture. Let's review the course objectives and structure. We will start this training by talking about the traditional monolithic software development style dominating the software industry until recently, and the challenges associated with such old school design in the context of the cloud. I'm going to use a simple example of an airline reservation system. It will be an essential background to understand the nature of the problem, why we are moving in that new direction. Then we'll start to talk about microservices. What are microservices? What are the building blocks of a single microservice? Like we have API gateways, application logic, and data store. Then we'll move to the microservice architecture from a macro viewpoint, and we will define it using some common industry characteristics like loosely coupled services, independently replaceable and upgradable, and more. Next section will be about the key advantages of using this development style, making this approach very appealing to modern cloud-based application, and also the challenges when using this new approach. As we all know, nothing is perfect. There are also disadvantages to a new method. Still, over the last couple of years, the market adoption of microservices is impressive. So definitely there is something interesting in this new approach. And finally, we will review the interesting Netflix case study in the context of microservices. At the end of each section, you can test your understanding with a quick quiz. Just to set the expectation in advance, the objective of the course is to teach students the microservice new approach, overall architecture, and main benefits. It's not a training on how to develop microservice application. Now, practically speaking, I highly recommend you to follow the lectures in the right order. I wish you a useful and interesting learning. See you in the next section. Our story will begin by talking about the dominating traditional way to develop applications that are called monolithic applications. And in a few minutes, we will talk about the meaning of the word monolithic. This monolithic software development style was used for many years in the software industry and still being used today. Now, to be clear, I'm not talking about desktop applications like PowerPoint. It's about the development of enterprise level applications, meaning applications that are used by multiple end users over the network to perform some complex business logic. Those applications are running on some backend IT infrastructure while using multiple software components and a variety of technology layers. It can be an internal, private, corporate application accessed by thousands of end users in some company. Think about an airport application used at the gates or check-in counters to schedule and manage incoming and outgoing flights. It is an enterprise level application performing multiple functions and accessed by people working in that specific airport. This application will be connected to thousands of real-time data sources. Or it can be a public software as a service application like we are using day by day. Think about services like Uber, Netflix, Waze, Facebook, Google search engines, and many others. Each one of them is a global service with millions of customers. You can imagine that the backend software running this kind of service at the global scale is quite complex with many building blocks, a variety of technologies, interface with other systems, and so on. So this is the type of application we will discuss while moving forward in this training course. Let's start to define the concept of monolithic applications. Think about an online airline reservation system to book flights via the web. Every airline company is using such a ticketing system, and multiple customers and agents can access such website at any given time. It should process the request, display updated prices, check tickets inventory status, while making sure that two people will not order the same seat, of course process payments, and so on. Again, it's a complex application. The software architecture of such a flight tickets application will look like a three-tier system. There will be a layer of front-end web servers to get requests from end users, for example using Apache web server. The second layer will be the running environment for the application business logic, which is usually a centralized application server. This application server will run all the needed modules of that application, like getting requests, checking inventory, display prices, process payments, update customer profile, and so on. This application server will process the request coming from the front-end web server, execute some logic, and retrieve and update data from the database. In most cases, the application business logic is developed using a unified language with a single base code. Let's assume in our example that it was developed using Java, which is a very common language for a backend application. So all required functions and modules in that application are done using a single Java base code. And this is the third layer. This centralized database is the application data store, holding any needed information like the available tickets per flight number and user profile, purchasing history, etc. All software modules running in the application server are basically sharing and using the same centralized database. If you are working today as a software developer or maybe as a system administrator, DevOps engineers, and so on, I assume you are quite familiar with such N-tier architecture. This very common software architecture is called monolithic applications. The word monolithic refers to something constructed of a single piece of stone. Like when looking at some interesting sculpture that you are amazed by the fact it was created from one piece of stone, a few hundred years ago. In the context of software development, this name, monolithic application, has started to be used to describe in a negative way one large piece of program that is performing multiple functions. In our example, this application server is a monolithic entity. All the logic for handling a request to book a ticket end-to-end runs in a single application server. Even if the application is divided into modules, as we can see here, those modules are sharing the same Java development language and the same running framework, and also the same centralized database. Now, this kind of N-tiers architecture is very popular and still useful. When a software project is starting very small, it makes sense to use a unified development framework across the system, and in most cases use the same components like the same database, the same application server, and so on. As I said, this kind of software architecture was used for decades in the software industry and still being used today. So what is the problem with such kind of architecture? In a typical monolithic application, different modules inside that application may share the same code or share the same data. When I'm saying shared code, it means that some function, libraries, or piece of code are used in multiple modules. And as a result, those modules are what we call strongly interconnected. If we change something in one module or in some place somewhere in the application, like in a shared function, it can influence other modules. We saw that the three-tier flight tickets application has a unified application server, which means that different modules are developed using the same language, like Java. And this is very useful because different modules can easily share and access the same code, the same function, the same libraries. The code is reusable and also unified across the application. The same Java language is used to develop all needed modules, so the developer's skill set can be focused on Java. Also, those modules will communicate with each other using in-memory calls because they are running on the same server as a function calling another function. And the big advantage here is that those in-memory calls between processes running on the same server are very fast, which is useful in many applications. However, and there is a big however here, if we change one of those interconnected modules, several other modules can be affected. There are no clear-cut boundaries between modules, and therefore it's not so easy to change the application base code. It is a shared code. The same is true for shared data. For example, two or more modules are accessing some customer profile tables from the same database. In our example, the booking flight module is accessing customer profile, and also the payment modules is accessing the same customer profiles. They are using the same data store. If we change the structure of the data store, meaning the metadata of the database, it can affect those two modules. Now, just imagine a simple scenario of adding another field to the customer profile database. Someone should go over the application code and check which modules across the application are using this specific customer data. Otherwise, there will be, unexpected result. In the next couple of lectures, let's talk about the specific challenges of such shared code and shared data in a monolithic applications. Any software application is good for a while until something is changing. New business requirements are coming, new requests from the end users, new technologies. We all know that all software applications are supposed to be updated one way or another. The key issue is about the time intervals between those updates. You can imagine that the concept of shared code and shared data being used in a monolithic applications is creating a tightly coupled connection between modules. So the ongoing software releases will be for the whole application, okay? All modules together as a single block, as a single monolithic. Using our flight tickets system as an example, let's imagine that a new feature is required in a specific module. And the development team, quickly created that feature in a couple of days. They are very quick. But this module is working and interconnected with other modules. For example, all components are using the same database. And if we change the database structure, the metadata of the data, then it can influence multiple components. In that scenario, the application should be tested end-to-end to see that everything is still working and functioning as expected, even though this is a very small feature. Also, we have to redeploy the entire application in the production environment, which means more system downtime for ongoing upgrades, more complaints from end users when the system is not available, and higher risk to break something during the system upgrade. If you will ask, any system administrator, it is a huge headache to upgrade a large, complex software. That's the reason that ongoing software releases for such enterprise level applications will be once in a year, maybe 2 times in a year. Release cycles are tied together because it makes sense to package many small changes, many features, a group of bug fix in a multiple modules and wait for the next big software release cycle. The key drawback is that a large monolithic application will be an obstacle to frequent deployments. Every ongoing deployment will be a complex to schedule, complex to perform, and with a higher risk on impacting the usage of that system, which at the end will discourage people from performing frequent updates. And in the software business, frequent updates are not nice to have, they are must to have, as things are changing very fast. Companies would like to use the concept of continuous delivery of software updates. Such an approach of once a year software release cycle is becoming less effective for many companies and organizations that would like to move much more quickly with their software tools. If a new important features is needed now, why wait 1 year for that new features? Companies would like to use the concept of continuous delivery of software updates, and monolithic applications are not really designed to handle such frequent updates. Let's talk about another scenario. Imagine a new developer just joined the company and he or she would like to perform some change and add a new amazing feature. Well, it's not going to be easy. This new developer must spend a huge amount of time to understand what's going on, explore unknown dependencies between modules before even touching the application code. Otherwise, he or she can easily break something. The situation is even more complicated when the amount of developers that are working on the same application is growing. Each developer is adding another piece of code and it's getting bigger and bigger. Now, because there are no specific and clear boundaries between modules, eventually the overall system modularity will break down over time. Going back to our example, let's assume that we would like to add a rating capability that will enable customers to provide feedback about the ticket purchase process and service during the flight, suggestion from customer, etc. We saw that our application is divided into modules as main functional building blocks. One module will be the user interface, the second module will be the booking flight process, payment process, another module will handle the rating and feedback from end user, etc. So the development team will open the application Java code and develop the needed features, maybe as a new module. Still, to be able to develop the features in time, we estimated that another development team should be added to the project. Let's assume each team is around 10 people. Now we have 20 people working on that application. Now, fast forwarding a year or two into the future, as more and more features will be added to that application, more people will be involved in that ongoing project, meaning more developers, more product managers, more QA engineers, more operation engineers, DevOps engineers, etc. As the complexity of the application is growing, more people are joining, and much more complex coordination between them will be needed. The problem with a monolithic application is that it prevents the development teams, from working independently. The teams must carefully coordinate their development efforts. Imagine an application started with 10 developers and now growing into 100 developers. It is a completely different story. So this is the second important drawback related to a monolithic application. At some point, it will become a challenge to scale the team and still be effective. The third major challenge about a monolithic application is related to scalability, or better call it limited scalability. Scalability is the ability to increase and decrease available IT resources to better match the actual load requirement on a specific workload. In case there is a bottleneck in a monolithic application, the solution can be divided into two main options. The first one is called vertical scaling, or also called scale up, which means adding more resources to an existing node. Imagine a web server is running on a specific virtual machine size. We can enlarge the virtual machine resources, like adding more memory, CPU power, storage capacity, network speed, etc. It is called scale up or scale down. Still, at some point of time, we will reach some limitation, like a maximum amount of memory or maximum amount of network bandwidth. It cannot scale forever. So we have another options for scaling. The second option is called horizontal scaling, or also called scaling out or in. In that case, it will handle the bottleneck by creating another parallel instance of the same node. If we had one web server, let's have two web servers or maybe more, and balance the traffic between them using a component like a load balancer. Now, not all components will support such scaling options, but it's getting very popular and useful options when talking about automatic and dynamic scaling in a cloud environment. So, everything is perfect with those two scaling options? Well, not really. In a monolithic application, the main problem is that the scaling granularity is limited. Imagine that we have 5 modules as part of some application running in the same application server. Let's say that one module, like module B, is creating a very high load on that server, which impacts all modules running in that server. Even if the problem is just related to only one specific module, we still need to scale the whole application server as one entity. In case we want to use horizontal scaling, then another full replica of that application server should be created. It is a solution, but not an optimized solution. This kind of scalability is basically a waste of computing resources in the world of elastic cloud computing. If we could break the system into smaller components that are running on separated IT resources, the scaling could be much more focused on specific localized bottleneck. Okay, so if we can run only module B on a separate IT resources, then we have the options to scale only that resources. Also, cloud native application, okay, and now I'm moving a little bit into the future, are supposed to run inside containers, okay, not virtual machines, okay, instead of using virtual machines. And again, a monolithic application is not really a good candidate to use such kind of virtualization technology, meaning containers. As a quick recap, I want you to remember that a monolithic architecture is still a very useful development method for small, medium-sized software projects. And many software projects will still use this development style in the future for many use cases. However, there are some major drawbacks when we are talking about large-scale complex applications that are supposed to be changed more frequently and to be able to effectively utilize a cloud environment. It is difficult to quickly deploy new features in an existing system, which is a critical business requirement in the digital data-driven business landscape. A change we made in a small part of the application requires the entire application to be tested and deployed. It is also a challenge to coordinate the ongoing task of a large group of developers because the dependency between modules and layers in that application. Releasing new features one time or twice a year in a production system is no longer fulfilling the business requirement of many companies. Those companies are looking for much faster software release cycles. Okay, this is like the innovation velocity and better capability to use elastic cloud infrastructure. Now, this limited ability to quickly add and change software features in a big monolithic application is driving companies to find an alternative, a better way or a new approach to develop and maintain applications. Finally, coming back to our main topic, this new approach is called microservices, and in the next section we'll start to talk about this interesting concept. In the previous section, we talked about the disadvantages or challenges associated with a monolithic enterprise level application. It was an introduction for understanding a little bit better the nature of the problem, so we'll be able to move on to the solution. Now we are ready to talk about an interesting new approach to develop application, meaning microservices. Okay, so what are those microservices? Let's define this concept at a high level as the first step before diving into the details. Microservices at the basic level is a software development architecture. That's it. It's not a new technology or a new market product. It's a new architecture on how to design, develop, and maintain applications. In this new approach, a large application is broken into smaller modular pieces, and those small pieces are called microservices. Each microservice is a single function module, meaning it is supposed to perform a single main activity, and this is where the name is coming from, microservices. A lot of small services that communicate with each other, and each service is supposed to do one thing and do it well. At the macro level, we have a complex application that is performing multiple functions while using a group of microservices. A simple analogy to microservices is a game we used to play as kids, meaning Legos. Each piece of a Lego is a standalone entity. We can take those little pieces as building blocks and put them together somehow to create a bigger module. Each piece can be replaced if needed, and a specific piece can be used to build a variety of modules. If you are a software developer today, you can jump back and say, what's the big deal here? Every big software is divided into smaller modules, and every module is divided into functions or objects. So what is so special with microservices? The answer to that question is that those microservices are completely standalone entities decoupled from each other with an explicit boundary per each service. Each microservice is like a micro application. Imagine many small boxes. Each box is a standalone microservice. One microservice is holding a unique content inside which cannot be accessed directly by other microservices. It has a what we call control boundary. Each box is developed independently and deployed in the production system independently. They are like, as I said, mini applications that communicate with each other to provide the functionality of a complete end-to-end complex application. Now, usually microservices are talking to each other using well-defined REST APIs. We'll touch that later. Let's use our airline reservation system as an example. In a monolithic architecture, the application is divided into modules, but all those modules are usually developed using the same framework. They are running on the same application server and are using the same centralized database. In a microservice architecture, we are taking the application and break it down into multiple services, microservice 1, 2, 3, etc. All microservices will be used together to create a more complex business logic. In the context of our example, there will be a microservice like booking flight, checking inventory, allocate seats, update customer profile, manage rewards, etc. Services will be organized around business domains, and each service is supposed to be a standalone unit that should be developed and deployed by the same team. Let's take a look at the building block of a single microservice in the next lecture. We can think about a single microservice as a small black box that is doing something specific, getting input or request from outside, perform some logic inside the box, and then return the result as output. It is similar to the concept of functions in programming. A function can get variables as input, perform some logic inside this using this input, and can also return something as output. But unlike functions that are based on the same code, the same language, the same running framework, here the services can be based on completely different language. Those services are separated. Each black box does not know anything on the inside of another black box, but they can communicate with each other over the network. The box analogy is used to emphasize that the microservice has a defined boundary. Also, the inside of the box can be basically a mini system that is based on multiple components. Now, if we will open as an example a single microservice black box and take a look inside, we'll be able to see three main building blocks. The first one is API gateway, the second one is application logic, and the last one is data store. Let's talk on each of those building blocks. The first building block is the API gateway. APIs are interfaces or access endpoints to a specific microservice. A microservice APIs receive a certain input as a request from outside, perform some logic, and then deliver a certain output using the API gateway. It is how the microservice box is communicating with other microservices. I'm sure you're familiar with the concept of internet communication. When I'm typing a URL in my browser, basically the browser translates this URL to a simple HTTP request being sent over the internet to a remote web server. This web server is providing a web API that enables to access the web pages in that web server. This web server is waiting and listening on a specific port numbers for getting request and response according to the content of each request. It's called REST-based communication. The famous HTTP protocol running inside the REST-based communication is using a group of methods such as GET, POST, and PUT. All the complex internet communication that we are using day by day is based on this simple but very useful concept. One side is exposing an API as an access point, and others can send requests over the network to this access point to get something. Now, microservices took this web connectivity concept and put that inside a microservice. Each microservice has some API gateway that acts as a front door to the microservice, and it's waiting and listening to requests from other microservices. As we said, the microservice black box should get and return data. So every microservice includes an API or maybe group of APIs written in a specific way and impose a set of rules on how to access it. Let's use our flight ticket application example. Let's say we have a microservice which allocate a seat inside an airplane to a specific ticket. So as input, it is expecting to get few parameters like the customer details, flight number, and the type of airplane. Those parameters will be the input to the API. The output will be the allocated seat number to that specific customer. Looking at the following diagram, another thing to keep in mind is that a single microservice can expose one or even multiple APIs. And maybe some microservice will not expose API at all, meaning it is just consuming APIs of other microservices. So in the context of API gateways, multiple combinations are possible. Let's move to the next building block. The next building block is the application logic, which is the brain of the microservice that is supposed to do something useful. The API gateway we already covered will trigger the inside application logic. As an example, think about a microservice that is supposed to get a picture as an input and return a text with the type of objects identified in that picture. The API will be used to trigger this microservice with a picture file as an input parameter, and the application logic will be used to process the picture and identify objects in that specific pictures. That's the complex process encapsulated inside a specific microservice. Finally, the microservice will send the identified objects as output through the API gateway. Now, one of the greatest benefits here is that the code developed for the application logic inside a specific microservice is completely independent. The team that developed this microservice can first of all select the best language to do the job to fulfill the task. In our example, the task is to identify objects in a picture. Okay, and they selected the Python as the best language to fulfill that job. And then they can change the code base as needed without worrying about other microservices that are using this specific microservice. The only thing that should always be consistent with other microservices is the way to access the API gateway. Now, as a side note, this approach is also called a polyglot programming, which means the practice of writing code in multiple languages to capture additional functionality and efficiency that is not available in a single language. The last building block is about the data, the gold mine of many applications. In most cases, the application logic will use some data stored in a database while performing the needed logic. If the microservice is, for example, check flight inventory, then the application logic should query some database and maybe also store something. That's clear. Now, in some cases, we may assume that multiple microservices can use the same data store as modules in a monolithic application that are using the same database. However, this situation is not aligned with the microservice approach. The best practices for microservice architecture will be that microservices should not share data store with other microservices, meaning each microservice should encapsulate its own data store, and other microservices will not be able to access that data store directly. They can, of course, access that data store indirectly while using the microservice API gateway. Again, if you are a developer today, you can say, are you crazy? For each microservice, we will now manage a separate data store instances. We will end up with too many data stores. So why we should consider this approach? Okay, there are two main reasons for doing that. The first one is related to the capability of developers of a specific microservice to change the data store without affecting other microservices. They can develop, test, and change things in the microservice data store, which can help to speed up the process of updating the microservice capabilities. Secondly, is that each development team can decide what will be the best database technologies to be used for a specific service or a group of services. One service can use a relational SQL database for a particular use case, and another service under the same application can use a distributed big data solution. Going back to the three microservice building blocks, meaning the API, gateway, the application logic, and the data store, we are getting a standalone services. Each service is like a separated mini application. They don't need to know anything about the underlying implementation or the architecture of other microservices. That's the reason why a single team can manage the complete life cycle of a specific microservice. So that was an overview at the micro level, meaning the building blocks of a single microservice. In the next section, we'll move on to the macro level and talk about the microservice architecture. In the last lecture, we saw the building blocks of a single microservice. Now we can move on and talk about the architecture of multiple microservices working together to form a complex end-to-end application. The microservice architecture is a method of developing application as independently deployable small modular services. Each service has its own unique and well-defined role. It's supposed to do something specific. Each service runs as a single or maybe group of unique processes. Those services communicate through a well-defined APIs over the network. Each microservice is supposed to be deployed, upgraded, scaled, and restarted independently. Now, the more low-level definition of a microservice architecture is a spectrum. There is no clear-cut definition for such architecture. Still, there are some best practices used in the industry today that we will use to describe this method, and that's the goal of this section. Let's say some company has a new, fantastic, interesting application to develop. How should they divide it into microservices? Should they use 10, 20, 100 services, maybe 200 services? That's a good question. Now, I'm not planning to make you a developer, but it is an essential to understand that one of the main challenges when moving to microservices is the decision on how to divide an application into services. What are the fundamental principles to slice up the application? So one of them is the size of a microservice. What is the leading business domain to be covered by this microservice? What kind of functions will be covered? How many people will be part of the team that will develop and maintain it? Trying to figure out how big an individual microservice has to be. In the context of defining the size of the team that will be responsible to a single microservice, some companies like Amazon invented the concept of limiting the size of a team that can eat 2 pizza boxes. Okay, sound like a joke, and I'm not sure it is a good, rule of thumb to all cases, but still it is used to emphasize that the team should be small, which also means that the complexity of a microservice should be limited. The scope of a single microservice should be narrow and focused on some single business domain and a small set of capabilities. In simple words, a service should do one thing and do it well, keeping in mind that those small services are working together as a group to create a more complex end-to-end application. In a monolithic application, we can divide, of course, the application into modular components. However, most development language used to develop those monolithic applications do not have a suitable mechanism for defining a clear, explicit interface between components. Basically, it's up to the developers to keep those boundaries as much as possible and prevent breaking the components' encapsulation. Eventually, it will lead to tight coupling, tight connection between components. One thing we change in one part can affect multiple other parts. In a microservice architecture, each microservice component is designed as a black box. It is like a black box because it is hiding the details of the internal complexity of that box from other microservices. There is an explicit boundary between the microservice black box to the outside. Each microservice will be developed with its own base code as a self-contained entity. It will not refer to any code outside the microservice boundary. So there are no hidden dependency. Any communication between microservices is only happening via a remote call mechanism with a well-defined APIs using the API gateways. In other words, we can say that microservices are loosely coupled between themselves. And this loose coupling is the greatest advantage of a microservice architecture. Different components in a microservice architecture can be changed, upgraded, and or replaced independently without affecting the functioning of other microservices, other components. More than that, services can be shared and combined easily with other applications. So there can be a situation that two different applications are using the same microservice. Okay? Think about a simple analogy like an electric bike with a battery. Okay? It makes sense to design the bike in a way that the battery will be easily extracted and replaceable as a separated component from the bike body. The same concept is essential in microservices. An application that was designed using microservices can, by definition, be broken down into multiple services and multiple components. Those components can be independently replaceable and upgradable without having to redeploy the entire application and basically compromise the integrity of that application. It is like a Lego game. In the traditional monolithic development approach, the development department is usually divided into teams that are like a mirror of the multiple tiers or multiple technologies in the application architecture they develop. And let me explain that a little bit more. We will see a team which is focused on the application user interface, UI's team, like HTML web developers. A separated team related to the database infrastructure, like big data experts. Another team may be organized around APIs for that application. A team for server-side logic, and so on. The focus is on technologies and layers. It's looking like, for example, like the following diagram. There is a UI specialist, middleware specialist, and DBAs. The most significant disadvantage here is that when there are multiple teams, every change in the application can lead to a cross-team project that should be orchestrated very carefully, involving several different teams working on that specific change. If you think about it for a second, the organization structure is organized according to the monolithic software architecture. Now, this strong linkage between the organization structure and the software created by a specific organization was actually captured many years ago by a person called Melvin Conway, saying that any organization that designs a system will inevitably produce a design whose structure is a copy of the organization communication structure. Now, over the last few years, multiple organizations understood this strong linkage between their internal structure and the software they produce and decided to embrace new structure. Companies like Netflix and Amazon were really the industry pioneers. And yes, it's based on microservices. A microservices architecture is changing the monolithic application approach entirely, okay, in this context. Instead of looking on technology or people's skill sets as a way to organize teams, let's first of all organize the building blocks of an application around business capabilities. What kind of business capabilities the company is trying to create? And based on the required capabilities, the application will be divided into services. But not just that. Such services can utilize at the end a broad stack implementation of software for a specific business area. Okay, the same microservice can include user interface, some database storage technologies, some business logic, and so on. So, as a result, the teams that are divided according to services will be actually cross-functional, including the full range of skills required to design, develop, and deploy each service. Each team will be responsible for a small part of the overall system. Each team will have multiple skill sets, so they will be independent. For example, a UI developer, a backend developer, a DBA expert, an operation engineer on the same team. If something should be changed in the UI or the database, there are team members with the needed skill sets. As a result, such independent teams can own the whole life cycle of the services they create, managing services as small products and with a higher degree of autonomy compared to a large team with more monolithic base code. I'm working as a solution manager, or also called pre-sales manager, for many years in the software industry. And when talking about software modules as products, it is usually connected to the commercial side, meaning each module, each software module will have a license cost and will be presented to customers as a product. Now, when managing a module as a product, it actually helps to create the important linkage to the business requirements. Instead of looking at a module as just a set of functionalities, there is an ongoing effort to adapt and also enhance the software module according to some roadmap. Now, the same approach of managing products in a monolithic applications, handling big modules, is also useful at a smaller scale with small microservices. When each service is operated as an internal product, it will have a dedicated roadmap enabling a separated, evolving path with a strong linkage to the business requirements. Each microservice team will be focused on making the service useful and continuously updated according to ongoing new requirements. The second issue is related to DevOps. In traditional application development, there is a clear line between the team responsible for the application development, meaning all kinds of developers, on one side, and the team responsible for the actual deployment and daily operation of that application in the production environment. Any update to the software is at the end like a mini project. It is starting with assembling the needed resources, meaning the project team, and the first milestone will be, of course, developing the new features in that application, then perform some testing, and finally, when it is ready, it will be handed over to the operation organization. Okay, take it and deploy it in the production system. And probably after a while, the project team will be reallocated again to other projects. It's the structure of most organizations. Now, the microservice architecture is aiming to avoid this one-time project approach and use a new model that each team will be responsible for a specific microservice and manage it as an internal product over its full lifetime. As Amazon coined the notion, you build, you run it, emphasizing that a development team should take full responsibility for the software in the production environment. Maybe you heard about it, but this principle is also known as DevOps, development and operation working together, so the developer will also be involved in a daily interaction with end users and ongoing production issues. Many companies are actually adopting this organizational structure as a critical prerequisite to use the microservice architecture. Another critical aspect when moving to a microservices architecture is how to implement the intercommunication between them. Now, this lecture is a little bit more complicated, so try to stay with me as much as possible and don't worry so much if it's not, 100% clear. I try to simplify that as much as possible so we can get the main concept. We already talked about it, if you remember, from previous sections, that in a traditional monolithic application, different software components will be in the same process, or maybe in multiple processes running on the same server. And the communication between them will be based on in-memory calls, like function A is calling function B. Now, on the other end, microservices are supposed to be separated between each other with a clear boundary. And in some cases, each microservice will be maybe also distributed across multiple instances. So it is raising a fundamental question how microservices should communicate with each other. What is the best way to exchange messages between them? Now, there are two main message exchange patterns that can be used. The first one is called request response, and the second one is called observer pattern with a message broker. Let's see each one of them. Starting with the first one, request and response. When looking at the structure of a microservice, we saw that each microservice exposes access endpoints that can be used by other microservices. It is similar to the famous client-server model being used to deliver web content in the internet. The microservice endpoints are used to process information and apply the internal logic in each microservice. All the smart part is happening at the endpoint inside the microservice. Each microservice can call any other microservice. It is decentralized communication. The communication channels are just dumb pipes used to deliver the input and output of each microservice. Using this request response model, one service sends a request and expects immediate response. The response can be acknowledgement, like telling, yes, I got your request, thank you. Or it can be specific expected output from that service, like the name of the customer is John. Now, in real life scenario, some microservices will need to handle high traffic load, so maybe few instances of the same microservice will be created, and then some load balancer component will be used to balance the incoming traffic between them. We have the originating service that is sending something, and then a load balancer is getting the request and decide where to route it based on the load of the backend instances of the same service. Okay, it's a very simple approach. Keep in mind that every communication here is always based on expected response, meaning one side is asking or sending something, and then the same side is expecting to get a response from the other side, meaning side A is waiting for that response before moving on. This approach is of course widely used. Think about a user interface for an application. Almost every action that is performed by end user is expected to be handled this way. Some user is trying to log into the system, then the service that is sending the user credential for validating a test is expecting to get the answer right now, waiting for the response, so it can be reflected back to the user that is trying to log right now. However, there are some cases that this synchronized method is less effective. Not every action or use case in a software application should be handled as a workflow, step 1, step 2, step 3. There are some cases that process should be a parallel workflow. Now we are getting to the second approach of handling communication between microservices, that is called observer. Okay, or observer pattern with a message broker. The observer pattern is used to implement a distributed event handling system. This is the message broker. And the concept is very simple. The message broker is used to create multiple data pipelines. To each data pipeline, we can connect producers, which will be the data sources creating the messages in that specific pipeline. And on the other side will be consumers, which will be listening to new messages coming in that specific pipeline. Maybe you heard about it. For example, the Apache Kafka solution can be used as a message broker that is used to implement event-driven system between components in a complex architecture. Now, going back to microservices, if I will explain the process here. So microservice will send a message under specific topic to a message broker. Other microservices will subscribe to the message broker to automatically get notification that a message is waiting for them under a specific topic. Okay? When implementing such message broker, multiple microservices will subscribe to one or maybe more event topics that they need to respond to. There are, of course, multiple advantages for such event-driven system. First of all, the microservice that is producing a message does not need to know which services should handle this message. It basically publishes the data to the message broker, and that's it. Secondly, the message broker will manage those messages in a dedicated queues. If the microservice that should process the message is busy right now, the message will wait in the queue until it will be less busy. And also the producer is also not handling failure and retries. It is just, simple mode, fire and forget, and all the such problem will be handled in the message brokers layer. In addition, this is the third one, new types of consumers can be added easily without the need to change anything in the producer side. And the last one is that the consumers don't need to query the message broker for messages, as the system will automatically notify them. Until this point, we mapped in great details the building block of a single microservice, as well as the key characteristics of a microservices architecture. In this section, I would like to talk about the value of microservices, meaning what are the benefits while using this development method. We saw that the microservices architecture is based on the approach of decomposing or breaking an application into different smaller modules called microservices. Those microservices are decoupled from each other. Each microservice has a clear business domain, boundary, and a specific scope organized around business capabilities. They are like black boxes modules with well-defined interfaces. The first key benefits of microservices is that they can be independently developed and independently deployed. And this is a killer advantage compared to the one big monolithic application old school approach. Different teams, handling different microservices can work in parallel to each other according to ongoing requirements and with different velocity. One service may have many development iterations because of a major functionality gap, while another service may have fewer changes because it's more mature. Those services are managed as almost as separated mini products, each one with a dedicated roadmap. This approach is letting each team to be more agile and minimize the required coordination between a large group of people. Now, looking from the developer perspective, an application written using microservices will be just as complex as a monolithic application. The key point here is that because a monolithic application is handled as one big entity, each developer must understand this application as a whole, end-to-end, which is of course much more complex. On the other end, with microservices, the developers can focus on smaller components, smaller chunks. Think about the process of debugging a single microservice. It will be much easier compared to finding bugs, finding problems in one big application. If I will summarize, one of the major benefits of microservices is the speed and parallel development capability. Development teams can work on different parts of the same application at the same time in a different speed. The next important benefit is related to deployment, meaning the process of upgrading an existing system in production. In monolithic application, it is usually a nightmare for system administrators. First of all, they need to allocate something that is called maintenance window to power down the system for the upgrade process, which is not an easy task when many end users are using the system. Secondly, when doing a full system upgrade, usually, bad things will happen, as the reality is always more complex than a set of predefined testing scenarios. In a microservice architecture, the ongoing deployment is supposed to be more simple. Each service can be deployed in its own timeline without complex dependencies. When some change is required in a certain part of the application, only the related services can be modified and redeployed without redeploying the entire application. Putting aside for a second the capability to deploy microservices independently, as we saw in the previous lecture, let's talk about the business benefits. We are in the middle of a huge revolution in many industries right now. All of them understand the power of controlling and managing their data much better. There are a growing amount of business models that are completely digital driven. They are based on data. And data is collected and managed by software. Software is everywhere. Customers and IoT machines are sharing data and accessing products and services from a growing amount of access points. To be competitive in this digital-driven market, organizations must be able to respond faster to new requirements, new markets needs, and ongoing changes in the business landscapes. Things are moving faster. Microservices is a solution to that challenge. Microservices were developed as a way to divide and conquer. Each microservice base code is managed by a small and agile team. The dependency between microservices having on one another is their APIs. And as long as the teams are maintaining backward and forward compatibility, each team can work in release cycles that are decoupled from other teams. There are, of course, some scenarios where those release cycles are actually coupled, when one service depends on another or depends on a new feature in another service, but this is not the usual case. By using microservices, organization can perform much frequent and faster delivery of software changes. By releasing application much faster, different business owner inside each company can get quicker feedback from customers or end users and make faster adjustments. Adjustment, of course, to the software code, but it also can be to the business model or the target audience and so on. It is a faster closed loop scenario. More than that, because the application is divided into microservices and each microservice is directly driven from the business domain, it may be possible to measure the cost and revenue of each microservice, like the cost of development resources, IT resources in the production system, etc. Business owners can better track where the money is going and how to better allocate resources, moving them from low impact business domains to higher or better business domains. With a monolithic one big application, any changes will require a full build and deployment of the entire application, which will slow down the release cycles. With microservices, we need to redeploy only the service or services that were modified. It is more granular release per service or small group of services. This approach speeds up the ongoing release process. The downside is that there are more release cycles to manage and orchestrate, and of course this process must be automated somehow. This is moving us to the next topic in this lecture, which is continuous delivery. To be able to effectively manage the release cycles of a large number of microservices, we have the option to automate the ongoing process of integration and deployment of software releases. It is called CI and CD, okay? Continuous integration and continuous deployment. Instead of releasing versions every few months, as we saw in a monolithic application, let's look on that as a continuous process, releasing new software features every few weeks, days, and even few hours if needed. The key benefit of microservices is that they work really well with continuous integration and deployment. In a complex application comprised of many services, different services evolve at different rates. So it makes sense that each service will have a unique continuous integration and delivery pipeline with ongoing upgrades. Okay, like service A version 2, service B version 6, service C version 3. Each service is continuously developed and separately maintained and independently deployed in the production environment. Continuous integration is also aligning to the concept of handling a microservice as a product that should be improved and optimized quickly. It should have its own source code management repository and its own delivery pipeline for ongoing builds and deployment. Developer can implement bug fix and enhancement at any time without waiting for major application upgrades, something that is not really possible in the monolithic approach, where the speed of each release is basically reduced to the rate of the slowest moving part. In a monolithic environment, the code for the application is typically developed in a single language. The developer will select some uniform technology framework. If the development team selected Java as the unified development framework, then probably most of the modules in that specific application will be developed in Java. They are expert in that language and they will keep using it. It will be always a compromise between capabilities and the desire to unify the framework as much as possible. This is true not just for the development language, of course, it can be for any other unified component as part of the application. For example, if we selected Oracle as the main database, then it will not be so easy to replace it in the future for handling new requirements, because many modules are using the same database technology. It is a centralized data store. In a microservice architecture, there is no centralized components being used by multiple microservices. It's the other way around. Microservices are decentralized in the way they are developed, deployed, managed, and operated. Each microservice has its own business logic and its own data store. They are, of course, composed together to form a complex application. This decentralized approach has a huge benefit for developers because microservices do not need to be written using the same programming language. One team that is handling a specific microservice can select, for example, Java as the language and MySQL, a relational database, as a data store. Another team handling completely different microservice under the same application can select, for example, Python combined with MongoDB NoSQL. Each one of those teams has the freedom or flexibility to use the best fit technology for the required functionality, helping to solve their specific problems. Or in other words, select the best tool for doing the job. There is no standardized technology pattern unified for all microservices. It is also called decentralized governance. And the fact that small teams can almost autonomously select the best appropriate technologies, frameworks, and tools for their domains is basically essential driver for innovation. The next benefit I would like to talk about is related to the concept of scalability. Scalability is the ability to rapidly and continuously change resources according to the current capacity demands. If the load on some application is growing and reaching at some point in time the maximum capacity of the allocated resources, then the system performance will be degraded. Think about a website that is designed to handle 1K users per minute, and suddenly 100K users are trying to access the same site. Probably most of them will not be able to access this specific site. It is a scalability challenge, and it is happening everywhere in many software applications. Can you imagine that Amazon site or Google Maps service will be down because of a performance issue? In today's business landscape, it is almost unacceptable. Online services are expected to be available 24 hours, 7 days a week with minimum downtime. Companies are putting a lot of focus on user experience, and performance issues are a critical factor to consider, monitor, and manage. The good news is that virtual IT resources provided over a private or a public cloud service changed completely the way we tackle the issue of scalability. And today, more than ever, cloud native applications are expected to be able to utilize the elastic capability of cloud resources. In the monolithic approach, we have multiple modules running on the same application server. Let's take a simple example of an application with only 3 modules, A, B, and C. All of them are based on Java and are running on a WebLogic application server. If the load on module A is growing, then we need to do something. And we already talked about it in previous sections. There are 2 well-known options, scale up or scale out. Now, those scaling options are very useful. However, if you think about it, it's not an optimum best solution. First of all, we need to select a virtual server that will handle all 3 modules, A, B, and C. Now, if module A is based on CPU intensive workload, and on the other side, module B is more memory intensive workload, then the overall virtual server can be quite expensive or maybe less optimized for both of them. Another issue is that a load on one module can influence the performance of other modules because they are sharing the same resources. However, if the load is only related to module A, for example, why should we scale resources that are related to other modules? It's basically a waste of IT resources. All those issues are solved when using microservices. Since in microservices architecture, an application is divided into several different services. Each microservice can run on dedicated resources, providing the capability to scale individual microservices according to specific localized bottlenecks in that specific service. The individual microservices can be individually scaled. It is more granular scaling and therefore more optimized scaling, which is making an application more cloud native. Let's use our example of the airline reservation system. We will have multiple services when using microservices, and each one is responsible for a specific function or business domain. For example, one service might handle online check-in, while another service will manage the online booking. Okay? Per each service, we will have multiple instances according to the required capacity. Each instance of the same microservice is created when it's required, and when the extra instances become redundant or underutilized, then they can be destroyed to save resources. In a cloud environment, everything is monetized. It is usually a service we are paying for according to the actual allocated resources. So if we pay for each instance, it is not making sense to keep them when they are not needed anymore. It is also useful for better isolation and overall system resiliency. If a specific component in some microservices malfunction, we can quickly spin off another instance of the same service using containers while the rest of the application continues to functions. The most important thing I would like you to remember is that a microservices-based architecture can better leverage the power of a cloud environment and effectively handle less predictable workloads. We all know that nothing is perfect. Microservices architecture has excellent advantages and its useful approach for complex cloud-native applications. Still, there are some challenges, problems, and trade-offs associated with such approach. Let's talk about the main challenges when moving to microservices. The first challenge is related to the overall software architecture. On one side, the services are becoming more simple and smaller. Smaller modules are easier to design and code. However, the overall architecture is getting more complex as the number of services grows. It's a trade-off. Smaller pieces, but much more pieces. Also, those services are working in a distributed architecture, so it is an additional complexity of a distributed system. In a monolithic architecture, the complexity and the number of dependencies between modules reside inside the application base code. While in a microservices architecture, the complexity moves to the external interaction of multiple services. Developers have to put additional effort into implementing the best mechanism of communication between the services. If you remember, we talked about it in the smart endpoints and dumb pipes lecture. Let's say we have two services, service A and service B, and the selected communication channel between them should be direct integration, meaning not using a message broker in the middle. Each service can be based on multiple instances that are created automatically by the cloud environment according to ongoing changes in the traffic demand. Okay, this is horizontal scaling, creating more instances of the same service. Now to the question. When a new instance of the same service is created or destroyed, how other services will know which instance is relevant when they are trying to call that specific service? Service instances will have dynamic locations. Think about a REST API request. Service A would like to call some API gateway of a service B. Now, what will be the IP address and port number of the remote instance? Without going to the low-level details, the answer is that a service discovery mechanism should be used, or a message broker, DNS or load balancer component, and so on. There are, of course, several options to consider. Services are communicating with each other over the network. Those remote calls between services are actually more expensive in terms of resources than in-process calls in a regular monolithic application. So network bandwidth and latency is something to take into account. Think about a situation of two services that are located in different two data centers. When they communicate, there will be some latency between those data centers. So this is something to take into account. Monitoring a software application in a production environment is an extremely important practice. Collecting logs, metrics, and alarms from multiple layers. Now, when using microservices, there can be hundreds of microservice components and instances. Some of those services may not be in the same server or the same cloud environment. It is a distributed as well as dynamic environment. In the context of monitoring, it is becoming more complex to analyze telemetry data being collected from such dynamic distributed environment and, for example, pinpoint on faulty services or identify potential performance problems, monitor the overall system health, and how to debug interaction across the system if you have so many microservices. Okay, it's a challenge. The last challenge I would like to mention is related to resiliency. Failures will happen one way or another. Okay, this is the reality. It can be some hardware failure. It can be corrupted data, some external service downtime, and so on. There are many situations. And the application should be designed to be something that is called fault tolerant as much as possible. For example, making sure that if one service is down, it will not cause a cascading failure of multiple services. Now, probably it will be smart to identify where are the core services in a specific system, in a specific application that are basically used like a main junctions with high traffic going into them, and make sure that those specific core services are not a single point of failure. Okay, these are important considerations while designing and using microservices architecture. There are, of course, more things to consider when moving to microservices, and I assume more things will pop up as more companies are experiencing this new path. Nevertheless, it seems that for many companies, the benefits of a microservice architecture overcome completely the challenges associated when using this new approach. Hi and welcome back to our last section in this training. As a nice industry example, I would like to talk about the Netflix case study in the context of microservices. As you probably know, Netflix is a media service provider and a production company. Their main business model is a subscription-based streaming service which offers online streaming of films and television programs. According to Wikipedia, as of 2019, they have over 148 million paid subscribers worldwide, including myself. It is a global service, and I would like you to think for a second about the software application and underlying infrastructure Netflix is using to operate and maintain to be able to provide such a high quality service worldwide. In the context of microservices, Netflix was one of the first companies that identified that their existing monolithic application architecture is not the best solution for handling their streaming services. This is their main data center back to 2000, give or take. In this diagram, we can see a classical traditional software architecture. We have end users like customers requests coming from the internet that are going into a load balancer, which access a reverse proxy front-end web server. Here it's based on Apache. And then this web server is accessing a Java application server, which is based on Tomcat Java environment. In this application server, they had a single big application called Java Web, developed by Netflix team that was handling all required functions for their services. The application server was connected to a centralized Oracle database using JDBC, and then interconnected using a DB link to another Oracle database for handling billing information. As you probably guessed by now, they had several challenges with this architecture. The first one is monolithic code. This is the Java web application they developed. All development teams in Netflix were working on the same base code. And when some change caused a problem, it was very difficult to trace and troubleshoot the problem. And because of that, slowing down their capability to keep adding features and upgrade the code as needed. Okay, classical example. Secondly, it was a monolithic database, something that is very common for many applications. In their case, it was one piece of hardware running one big Oracle database. You can imagine that when this database went down, everything went down. It was a single point of failure. Also, it was a challenge to scale such database. Those days, the only options was to perform vertical scaling, meaning scale up by finding a bigger hardware machine, which is a very expensive approach. They had also problems to match the resources to the growing demand and usage patterns. And the last thing was that it was tightly coupled architecture. Everything was deeply interconnected. For example, many application modules were referring to the same database schemas because they used a centralized database store. Modules were connected in many in-process connections, making the base code one big spaghetti. Every change was a huge effort for the engineering team, and as a result, Netflix as a company was suffering from slow progress and lack of agility when it comes to releasing new software features. Because of those four main problems, they decided eventually to build a completely new software architecture based on microservices. They decided to create small services that handle separated business functions. Each function has a self-contained service with a well-defined interface. This diagram represents in high level how customers are accessing a very large edge layer with smart load balancing and traffic routing capabilities. And then Netflix API's gateways are used to access a variety of microservices to fulfill requests. For example, recommendation microservice is used to provide a personal recommendation per each subscriber, like a movie list. There are also infrastructure services like routing, so microservices can find each other and so on. So this is about Netflix. There are of course more examples of companies that are already using microservices or paving their way in that direction. Overall, I think Netflix is a very interesting and nice case study. Microservices architecture is a huge step in the software development industry. It started with the big players like Netflix, Amazon, Google, and others. Over the last couple of years, it is getting spread around as smaller sized companies are adopting this new approach. I'm working in a company that develops software products and solutions for the telecom industry, and I can see how customers are pushing software vendors to support microservices in their off-the-shelf products. Those customers are looking for software products that can be implemented in a cloud environment. So this trend is coming from multiple directions. In this training, we talked about the old school software development style called, in a negative way, monolithic applications, meaning applications that are one giant base code written in the same language, and specifically the challenges and limitations that companies are facing while using those applications for multiple use cases. All those problems created the right conditions for using a new approach, meaning microservices. Microservices are the foundation for cloud-native application, so cloud computing and microservices are two trends strongly connected. A single microservice is like a black box with three main components: API, gateway, business logic, and data store. Each service has a specific function encapsulated inside that service, and a group of services is used together to form a complex application. Those services are decoupled from each other, separated, and therefore introduce multiple advantages while using them in a software architecture. They can be developed, deployed, scaled, and maintained as almost separated mini applications. Each microservice can handle a specific business domain, and a dedicated team has the option or advantage to manage the complete life cycle of a particular service. This new approach supports the market demand for frequent software release cycles and also the requirement to implement application in a dynamic cloud environment, applications that are more cloud native. That's a quick recap to things we learned during this training. I want to thank you for watching this course. I hope that you enjoyed it and learned a few things along the way. I hope to see you again in my next training course. Bye bye.